In this video, we'll consider the classical Weierstrass representation, which makes minimal surfaces in R3. We will then reformulate a little bit this representation in a more modern and compact way and make our first explicit examples. Finally, we will have a look at the period problem in order to make examples of minimal surfaces with non-trivial topology. So what is the Weierstrass representation? Some notations first. In this video, we'll consider first D, a domain, simply connected in the complex plane. And we'll consider that our surfaces are actually given by maps F from the domain D to the Euclidean 3 space. And these maps are smooth immersions. Moreover, we will always consider that F is conformal, meaning that if you take two orthogonal vectors in D, which have the same length, then the derivative of F will map them into two vectors of R3, which are still orthogonal and which still have the same length. Now, Weierstrass in 1866 proved the following nice theorem. If our conformal immersion F is minimal, then there exists a holomorphic one-form omega taking value in C, and a meromorphic function G from D to C, such that up to translations, F is given by the following formula. So you compute using G and omega this three-dimensional complex vector, then you take a primitive of each component of this vector, which you can because D is simply connected, no multivaluation here. And then taking the real part of this vector gives you a map F from D to R3, which is minimal. And the nice point of this theorem is that any such data G and omega gives rise to a minimal immersion. So let's make our first example and take the simplest possible non-trivial G and omega. Taking these G and omega on the simply connected domain D in the complex plane gives you a minimal surface once you put these G and omega into the Weierstrass formulas. And because the Weierstrass theorem is actually an algorithm, you can, of course, implement it into a computer, which is exactly what Nick Schmidt did in Berlin with his software XLab, making nice pictures of minimal and CMC surfaces. So let's have a look at XLab and what it gives if you put that as an input data. This is what you get. Maybe you know it, it's called the Enneper surface. And this is the simplest non-trivial minimal surface that you can think of beside the plane. Again, all the pictures that I will show you are made by Nick Schmidt with the software XLab. Now, maybe you're like me and you don't really like these formulas, 1 minus g squared, I times 1 plus g squared. I never managed to remember them. So let's rewrite this Weierstrass representation in a more compact way. For that, a nice solution is to identify R3 with the three-dimensional real vector space SU2. So SU2 is composed of 2 by 2 complex matrices which are anti-Hermitian. Even if the matrices are complex, this is a three-dimensional vector space. Now you can go one step further and identify the Euclidean quadratic form by taking the determinant of the matrix in SU2. And you can even go one step further and encode the vector product in R3 with matrices in SU2 using this formula. With this identification, SU2 is really the three-dimensional Euclidean space. Now we can rewrite the theorem of Weierstrass. If our immersion, which is conformal, is moreover minimal, then there exists a nilpotent holomorphic one-form eta from D to the complexified SU2, such that, up to translations again, the minimal immersion f is given by this formula. And conversely, any such potential eta gives rise to a minimal immersion. A little remark. SU2 is a three-dimensional real vector space composed of anti-Hermitian matrices. You can complexify this three-dimensional vector space and get the set of matrices which have trace 0. As a matrix set, this is SL2C. But I did not write it as SL2C because I have to take at some point a real part. And what I mean by the real part is not the real part of the entries of the matrix that is here. What I mean is the anti-Hermitian part using this identification. Let's make the NPR example with this representation. Well, we need a nilpotent holomorphic one form in the form of a matrix, eta. And here is the explicit formula given exactly the same surface as you saw before. Eta is holomorphic, you can check that. It is also nilpotent, you can check that. And it has null trace. Now, with this potential eta, you can take a primitive on a simply connected domain, and then take the real part of the result. This will give you a minimal immersion into SU2, which you can identify with R3. So far so good. This method is very useful if you want to make simply connected minimal surfaces. But obviously, the non-trivial minimal surfaces are not simply connected. And if you take a non-simply connected domain, then this step will lead to problems. So let's have a look at that. What happens if instead of taking a simply connected domain D, you take a Riemann surface M, which is not simply connected? Then, because the first part of the Weierstrass representation involves taking a primitive, you cannot do that anymore. You have to take an integral. And in order for this integral not to be multi-evaluated, you have to consider the universal cover of M by M tilde. And I will call the projection from the universal cover to the surface pi. In order to take an integral, you have to take a base point z0 in M tilde, and then your immersion f will be only well defined not on the Riemann surface M, but only on its universal cover M tilde, via the same formula as before. Take your potential eta, take an integral of it, now you have defined a map from the universal cover, take the real part of this vector, and you have a map from M tilde to R3. Below is the simplest non-trivial example you can think of. As a non-simply connected Riemann surface M, take the complex plane minus 1 point. As a base point, take any point that lies above 1. And for your potential, you can take this one. Putting all these data into the Weierstrass representation, you should have a minimal immersion. Let's have a look at that. So this is what you get when you take as input data the potential and the Riemann surface that I have given you. You see that this surface is minimal, it's called the helicoid, and it's not well defined on the one-punctured complex plane. It is only defined on its universal cover. But is there a way, starting from a non-simply connected Riemann surface M, to make an immersion which is well defined on M and not only on its universal cover? The answer is yes, and let's have an example. This is nearly exactly the same data as for the helicoid, with the small difference that I have put an I coefficient here. But this potential is still holomorphic and nilpotent, and so if you put that into the Weierstrass representation, you should still have a minimal surface. Let's have a look. And indeed, we have a minimal surface that is now well defined on the complex plane -1 point. This is called the catenoid. Actually, instead of putting an I here, I could have put any unit complex number, lambda. Doing that is called considering the associated family of a minimal surface, and this lambda is called the spectral parameter. So now, taking this Weierstrass data, we should have a one-parameter family of minimal surfaces, indexed by lambda in S1. Let's have a look. This animation, again made by Nick Schmidt, shows the associated family of the helicoid. As lambda runs along the unit circle, you see various minimal surfaces, and only 2 of them close, giving 2 catenoids. Let's look at another example to see what can happen with this period problem. Here I take as a Riemann surface the Riemann sphere -4 points at plus and -1 and plus and -I. As a base point, I take any point above 0, which is in M, and as a holomorphic potential, let's take this one. So you see it has simple poles where you have punctures on the Riemann surface. Except if I tried to solve some period problem here, there is little chance that the induced minimal surface given by the Weierstrass representation will be an immersion from M to R3. But still you can make it so the periods at plus and -1 are the same, and the periods at plus and -I are the same. Let's see what surface it will give. This is the surface given by the Weierstrass data I just showed you, and it is called the second Shirk surface. It is simply periodic in one direction, and it infinitely extends in this and in this direction. It has infinite genus and looks like 2 planes with an infinite number of holes between them. Last but not least, let me talk to you about the Costa surface, discovered by Costa in 1984 and showed to be embedded 1 year later by Hoffman and Mix. This is a complete embedded minimal surface of genus 1 with 3 ends and finite total curvature. Let me show you a picture of it. This is the Costa surface. And having pictures of it was actually quite important in order to prove that this surface is embedded. It turns out that the Costa surface actually is one member of a huge family of minimal surfaces, and that you can change the genus of the Costa surface, and you can also change the neck size of the handles. We will talk about that in the last video. Okay, we have now a nice algorithm, the Weierstrass representation, which makes minimal surfaces in R3. Thank you for watching, and see you in the next video, where we will take a look at a generalization of the Weierstrass representation called the DPW method.